Look up at the night sky. What do you see? Stars, planets, maybe a distant galaxy. For thousands of years, we thought that was it. We thought the universe was made of the stuff we could see, touch, and measure. But we were wrong. Very wrong. It turns out that everything we can see, from the brightest star to the smallest grain of sand, makes up only about 5% of the entire universe. The rest is a mystery, a vast, invisible enigma that shapes everything around us, yet remains completely hidden from our view. It's a cosmic ghost story, and we're just beginning to understand the main character. This invisible stuff has a name. We call it dark matter. The name is a bit simple, but it gets the point across. It's dark because it doesn't give off any light or energy. It doesn't shine, reflect, or even cast a shadow. It's matter because it has mass, and therefore it has gravity. And that gravity is the only way we know it's there. It's like the wind. So how did we find this cosmic ghost? It started in the 1930s with an astronomer named Fritz Zwicky. He was looking at a huge group of galaxies called the Coma Cluster. He noticed something odd. The galaxies were moving way too fast. Based on the gravity of the stars and gas he could see, they should have flown apart millions of years ago. It was like watching a merry-go-round spinning so fast that the horses should be flung into the sky, yet they stayed perfectly in place. Zwicky realized there must be some extra, unseen mass holding it all together. He called it dunkle materie, or dark matter. For decades, this idea was mostly ignored. It was too strange, too radical. But then in the 1970s, another astronomer, Vera Rubin, found more evidence. She was studying individual galaxies and how they rotate. She expected the stars at the outer edges to move much slower than the stars near the center, just like the outer planets in our solar system move slower than the inner ones. But that's not what she found. You might be thinking, okay, so there's some invisible stuff out there. Why should I care? It's a fair question. Dark matter seems distant and abstract. But the truth is, without it, you wouldn't be here. The Earth wouldn't be here. Our sun and our entire galaxy, the Milky Way, would not exist. Dark matter isn't just a curious footnote in the story of the universe. It's the main author. It's the cosmic architect that laid the foundation for everything we know and love. It's the scaffolding upon which the visible universe was built, and it continues to hold everything together. Think of it like this. Imagine trying to build a giant sandcastle, but you only have dry sand. The grains just won't stick together. Now, imagine mixing that sand with water. The water acts as a binding agent, allowing you to build intricate towers and walls. In the early universe, regular matter, the stuff that makes up stars and planets, was like that dry sand. For a long time, the leading theory was that dark matter is cold. Now, cold in this context doesn't mean it needs a jacket. It's a scientific term that describes how fast the dark matter particles were moving in the early universe. Cold dark matter particles were slow-moving and heavy. They were like cosmic tortoises, lumbering along. Because they were slow, they could clump together very easily, even on small scales. This idea, called the cold dark matter or CDM model, has been incredibly successful. It explains the large-scale structure of the universe, like the cosmic web, almost perfectly. The CDM model predicts a universe full of galaxies of all sizes, from giant ones like our Milky Way, down to tiny dwarf galaxies. It suggests that big galaxies are built from the bottom up, by gobbling up lots of smaller ones over cosmic time. The model has been the bedrock of modern cosmology for decades because it works so well. It's like a recipe that produces a cake that looks just like the picture on the box. But when you cut into the cake, you start to notice a few things are slightly off. This is where the plot thickens. While the cold dark matter model works wonders on large scales, it has a few cracks when we look at the finer details. For example, the model predicts that there should be thousands of small dwarf galaxies buzzing around a big galaxy like our own. But when we look, we only find a few dozen. And this is where a different idea enters the kitchen. Warm dark matter, or WDM. What if the dark matter particles weren't slow-moving bulldozers? What if they were faster? Not super fast, like particles of light, which would be hot dark matter, an idea that has been mostly ruled out, but somewhere in between. What if they were warm? This means they were lighter and had more energy in the early universe, so they were zipping around much more quickly. Think of them as energetic teenagers, too restless to settle down in small groups. This extra speed makes a huge difference. In the early universe, when everything was much closer together, these fast-moving warm dark matter particles would have resisted gravity's pull. Their own motion would have allowed them to escape from small, low-density clumps. This phenomenon is called free streaming. It's like trying to herd a group of cats. It's much harder than herding sheep. The particles' speed would have effectively washed out or smoothed over the smallest dark matter structures before they ever had a chance to form. Only the biggest, most massive clumps would have had enough gravity to hold onto these zippy particles. Let's return to one of the biggest headaches for the cold dark matter model, the missing satellites problem. Computer simulations based on cold dark matter consistently predict that a large galaxy like our own Milky Way should be surrounded by thousands of smaller satellite dwarf galaxies. This is where the warm dark matter model shines. It provides a simple and elegant explanation for the missing cosmic villages. Remember the fast-moving warm particles and their free-streaming motion? This motion acts like a cosmic zoning law that prevents small structures from being built. The universe simply never built those thousands of tiny villages in the first place. It's like a recipe that was supposed to make 1,000 tiny cookies, but because the oven was too hot, the small dollops of dough melted and merged, leaving only a few dozen larger cookies. This solution is incredibly appealing to many cosmologists because of its simplicity. It doesn't require complex new physics or special conditions to make the dwarf galaxies invisible. It just requires changing one fundamental property of dark matter. The mystery deepens when we zoom into the very centers of galaxies. The standard cold dark matter model makes a very specific prediction about what we should find there. Because the cold particles are slow-moving, they can pack together very tightly under the force of gravity. The model predicts that this should create a sharp spike in density right at the galactic center, a feature known as a cusp. However, when astronomers carefully measure the distribution of matter in real galaxies, they often find something different. Instead of a sharp, pointy cusp, they see a flatter, more rounded distribution of dark matter at the center. So how do you catch a ghost? This is the challenge facing scientists trying to prove whether dark matter is warm or cold. Since we can't see it directly, we have to get clever. One approach is to try and catch the particle itself. Scientists build massive, ultra-sensitive detectors deep underground, shielded from all the cosmic noise that bombards the Earth's surface. They are essentially listening in complete silence, hoping to hear the faintest whisper of a dark matter particle bumping into a normal atom in their detector. So far, after years of listening, these experiments have found nothing. A profound silence. This lack of detection is starting to worry physicists. It's putting serious pressure on the classic WIMP theory, which is a prime candidate for cold dark matter. This is where the warm dark matter candidates come in. The most popular candidate for warm dark matter is a hypothetical particle called the sterile neutrino. Unlike the regular neutrinos we know, which are already incredibly ghostly, a sterile neutrino would be even more standoffish. If dark matter is a sterile neutrino, we need a different strategy. Sterile neutrinos are not stable. They should very rarely decay. When they decay, they are predicted to emit a single X-ray photon with a very specific energy. So the new hunt involves pointing our X-ray telescopes at places with a lot of dark matter, like the centers of galaxies and galaxy clusters, and looking for this faint specific X-ray signal. It's like searching a massive dark forest for a single specific type of firefly that only flashes once every million years. Another way to hunt for clues is to look back in time. We can't build a time machine, but we have the next best thing, the Cosmic Microwave Background, or CMB. This is the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. This ancient light is not perfectly uniform. It's mottled with tiny temperature variations. These tiny hot and cold spots were the original seeds that grew into the vast cosmic web we see today. Think of the early universe as a giant bell that was struck by the Big Bang. To really zoom in on the small-scale differences between warm and cold dark matter, astronomers need a different tool. They found one in something called the Lyman Alpha Forest. It works by using quasars, extremely bright distant galaxies powered by supermassive black holes, as cosmic lighthouses. The light from these quasars travels for billions of years across the universe to reach our telescopes. On its long journey, this light passes through countless invisible clouds of hydrogen gas that float in the voids between galaxies. Each time the quasar's light passes through a cloud, the hydrogen gas absorbs a tiny specific slice of that light. This cosmic barcode is a direct probe of the small-scale structure of the universe. Remember that warm dark matter smooths things out and erases the smallest clumps. This means that in a warm dark matter universe, there would be fewer of these small hydrogen clouds. By statistically analyzing the density of this forest, astronomers can put very strong limits on how warm dark matter could possibly be. To date, the studies of the Lyman alpha forest have provided some of the most stringent constraints on warm dark matter. The hunt for evidence is now moving into new, exciting territories, using clever techniques to map dark matter's influence with, honestly, unprecedented detail. One of the most beautiful methods involves studying what we call stellar streams. These are long, thin rivers of stars that are actually the shredded remains of small dwarf galaxies, or star clusters that have been torn apart by the gravity of a larger galaxy, like our own Milky Way. Another powerful technique is gravitational lensing. Powerful new instruments like the James Webb Space Telescope are designed to peer back in time, closer to the Big Bang than ever before. They are capable of spotting the faint light from the universe's very first galaxies. By finding out exactly when these first galaxies formed and how many of them there were, we can put the cold and warm dark matter models to the test. If Webb finds a universe teeming with tiny ancient galaxies from very early on, it would be a huge victory for the cold dark matter model. Imagine for a moment two pieces of art. The first is a sculpture made from countless tiny grains of sand, meticulously glued together to form a complex, gritty structure. The second is carved from a single smooth block of marble. From a distance they might look similar, but up close, their texture and origin are completely different. This is the choice between a cold and a warm dark matter universe. The temperature of dark matter might seem like a distant, abstract concept, but it could have a very real connection to one of the most profound questions we can ask. Are we alone in the universe? The answer could depend on the timing of galaxy formation. A warm, dark matter universe, as we've seen, would delay the formation of the first stars and galaxies. This means the universe would have to wait longer before it started producing the heavy elements like carbon, oxygen, and iron that are essential for life as we know it. Alright, let's bring this right back down to Earth. Why should you, a person living your daily life, care if dark matter is warm or cold? Because understanding the fundamental nature of matter and energy is the engine of all technological progress. The discovery of the electron over a century ago seemed like an obscure bit of physics. Yet today, every single piece of technology you use, from your smartphone to your microwave oven to the lights in your room, is based on our understanding of how to control that tiny particle. Ultimately, this is about more than just technology. It's about our place in the universe. Knowing what the cosmos is made of is fundamental to understanding who we are and where we came from. It's about the pure, unadulterated thrill of discovery. It's about looking up at the night sky and not just seeing points of light, but understanding the invisible architecture that holds it all together. We have journeyed through the cosmos, chasing a ghost. We've explored a universe that might be fundamentally different from our standard recipe. A universe that is a little warmer, a little smoother, and perhaps a little later to the cosmic party. The question of whether dark matter is cold or warm is not just a minor detail for scientists to argue about. It represents one of the biggest forks in the road in our quest to understand everything. But we are not at the end of the story. We are at a thrilling cliffhanger. The evidence is not yet conclusive. On one hand, the grand patterns of the cosmic microwave background and the thick, dense nature of the Lyman alpha forest provide powerful support for a cold, clumpy universe. On the other hand, the clues from our own galactic backyard whisper a different tale. The sparse population of dwarf galaxies, the potentially smooth cores of those that exist, and the hope of finding pristine stellar streams all point towards a gentler, less lumpy cosmos. So, what is the final verdict? Is dark matter cold or warm? The truth is we don't know yet, but the pursuit of that answer is one of the most exciting adventures in all of science. This isn't just an academic exercise. Unlocking the identity of dark matter will trigger a revolution in physics, on par with the discovery of relativity or quantum mechanics. These are the great projects of our time, the modern-day equivalent of building cathedrals or embarking on voyages to new continents. And so the next time you look up at the night sky, remember that what you see is just the tip of the iceberg. The real show is happening in the dark. An invisible cosmic web, a gravitational skeleton, holds everything you see in place. Is that skeleton built from slow, cold particles, creating a clumpy and chaotic universe? Or is it made of faster, warmer particles, resulting in a smoother and more serene cosmos? Finding the answer is the next great step in our human journey of discovery. The ghost is still out there, and the hunt is on.